today we're going to be starting Taylor and Maclaurin series, so we're going to start by doing Taylor series first of all. Right, so Taylor series are polynomial expansions, so that's x cubed, x squared, x to the power of 4, x to the power of 5, so there's no sin, cos, tan, exponential function, it's just polynomial functions, and they give good approximations to a function around a given x coordinate. Right, so it gives a good approximation at some point along the x-axis. So this can be used to find definite integrals, i.e. the area under a curve for functions that cannot normally be integrated or directly integrated. Right, i.e. right, if I've got the function e to the power of x squared dx. This is impossible. For me to integrate directly. Absolutely impossible. But if I was looking at that function and then say I wanted to know the integral between say 5 and 3. Right, so I wanted to know the area between between x equals 3 and x equals 5 of this function. Then right, so as I say, I wanted to go between 3 and 5, so if I look at around 4, right, because that's halfway between, and then integrate that function, then I would get a good approximation to the area between 3 and 5 for the function e to the power of x squared. Right? Finding Taylor series. Okay, now one little reminder is factorials. So if you see an exclamation mark, it means factorial. And if I've got 6 factorial, that would mean 6 times 5 times 4 times 3 times 2 times 1. Okay, if I've got 4 factorial, that just means 4 times 3 times 2 times 1. Okay, so formula for the Taylor series. So f of x is approximately equal to f of a, what's exactly equal to if we keep on going to infinity, f dashed of a, x take away a over 1 factorial, plus f double dashed of a, x take away a squared over 2 factorial, plus f triple dashed a, x take away a cubed over 3 factorial, plus all the way up and as far as you want it to go. Right, now A the series is centered around. Okay. Example number 1. Right, so find the first 5 terms of the Taylor series for f of x equals ln x centered around x equals 10. So what I want to do is find a polynomial function that exactly mimics the function ln x at the point x equals 10, so at the point 10 along the way. Right, so I want 5 terms. That means I need 5 derivatives, right? Sorry, I've got 5 terms. I want 4 derivatives. You always want 1 less than the number of terms that's being asked. Okay, so we start with f of x. So this is when I'm going to do my derivatives. This is where I'm going to get my coefficients. Okay, that's how I like to split it up. Right, so f of x equals ln x. So for the coefficient, all you do is you substitute in the centre around value. That's just ln 10. Okay, then f dashed of x, you differentiate ln x, you get 1 over x. And for the coefficient, we just shove in 10 again. Which I'm just going to leave as 1 over 10. Obviously I could write it as 0.1 if I wanted to. Right, now, if I want to differentiate that, the first thing I've got to do is rewrite it. Right. And then I can differentiate it, so I'm not going to get anything in there. So that gives me negative x to the power of negative 2. Right. And remember, that means negative 1 over x squared. So f double dashed of 10 is negative 1 over 10 squared, which is negative 1 over 100. Okay, so I've got the first function with 10 substituted in, the first derivative with 10 substituted in, worked at the second derivative with 10 substituted in. Remember, I need to find 4 derivatives because it's always 1 less than the number of terms I'm looking to find. Okay? Unless there's zeros involved. So f triple dashed. So to differentiate that, I'm not going to use that function, I'm just going to use that one there. So the 2 comes down to the front. 2x to the power of negative 3. That gives me 2 over x cubed. So now I can substitute that in. So f triple dashed 10 is 2 over 10 cubed, which is 1 over 500. Okay, f to the power of 4, or f, the fourth derivative, remember, right, we could write iv, but we tend to just write the fourth derivative like that. So again, I'm going to use that one, so that's going to give me negative 6x to the power of negative 4, which is negative 6 over x to the power of 4. That gives me 6 over, so that's 3 over 5,000 when we simplify it down. Right, so I have, how many coefficients do I have? Well, I've got 1, 2, 3, 4, 5. And that's how many I need. So I need to have 5 terms. Okay, so let's write down the formula. So f of x equals f of a plus f dashed of a, x take out a over 1 factorial plus f double dashed of a, x take away a squared over 2 factorial plus f triple dashed of a, x take away a over 3 factorial plus f fourth derivative of a, x take away a over 4 factorial. Right, so that would keep going. Now, two things is key, or the main thing that's key is my a is 10, so I'm going to substitute that in first. Plus right, so that's me there. Got f of 10 plus f dashed of 10, x take away 10 over 1 factorial. So in fairness, if you were going straight into this question that wasn't the first example, you could just go straight to this bit here. Right, substituting the 10 first. I'm just showing you where it comes from. Right, now, I've worked out f of 10, f dashed of 10, f triple dashed of 10, f of 10, f dashed of 10, f double dash 10, f triple dash 10, and a fourth derivative of 10. I worked all of those out down here. F of 10, f dash 10, f double dash 10, f triple dash 10, f the fourth derivative of 10. So let's substitute those in. So, right, so f of x equals f10, which is ln 10, plus f dashed of 10. Right, plus negative 1 over 100 x take away 10 squared over 2 factorial plus 1 over 500 take away 10 cubed 3 factorial plus, oops, sorry, that should be a negative up here. So your fourth derivative, that should be negative, missed it, that would be negative from there to there. What's that? Negative 3 over 5,000. Right. Okay, so just substitute in all those coefficients, because we found out the derivatives, we could get those 5 coefficients. Right, I'm just going to leave the ln 10 as it is. So the 10 comes down to the bottom alongside the 1, and 1 factorial is just 1. So 1 times 10 is 10. Right, here, well, that's not going to be a plus, it's going to be a takeaway. It's going to be x take away 10 squared over 100 times 2 factorial. 2 factorial is 2. So that's 200 plus x take away 10 cubed over 500 times 3 factorial. Well, 3 factorial is 6. So 6 times 500 is 3000. And finally subtract, oh, I've got a 3 on the top, 3x take away 10 square root of 4 over 4 factorial is 24, 24 times 5000 is 120,000. And then just check and see if you can simplify those fractions in any way. And there we go there. 3 over 120,000 is 1 over 40,000. So that is my Taylor series for that question there. Okay, let's have a look at a second example, and then I'll give you a few to try in the book. Right, what I kind of want to do is show you what this actually means. So let's see if I can do that just now. Okay, well, what I wanted to show you guys was what this actually means, right? So that function that I was asked to find the Maclaurin series for was ln x. Right, so that there is the graph of ln x. Very high tech and all, right? Now, what I'm going to do is, I'm going to type in the answer that we got there. So ln 10 plus x take away 10, brackets, over 10. So you can see 10, that's starting to pretty much mimic exactly the function in and around 10. Yeah? Right, let's see what happens with take away x take away 10 squared over 200. And now can you see it's even closer to the line than it ever was before, even down here. Plus x take away 10 cubed over 3000. Again, even closer again than it was before. Let's see if I zoom in a wee bit more. See, it's perfectly mimicking that line exactly. And if you put in the final term, it'll mimic it exactly. Right, it's going to be even closer. So what we're looking to do with Maclaurin series is effectively change something from an ln, a sin, a cos, a tan, an exponential, something like that, and make it a polynomial, right? ln 10 is just a number, right? So ignore the fact that's an ln, right? You would just get a number for that. So we're looking to create a function that's just made up of numbers and letter terms. It's not got a sin in it, it's not got a cos in it, it's not got a tan in it, anything like that. Okay? Okay, so let's have a look at example number 2. I know the video's jumping about a wee bit today, that's just so I can try and give you examples using the computer. Right, so find the first 3 non-zero terms of the Taylor expansion for f of x equals cos 2x around the point x equals pi by 2. So same thing. If I drew the graph of cos pi 2x, I would want to find a polynomial something just made up of x's, x squareds and numbers that mimics exactly that function at pi by 2. Remember, pi by 2 in degrees is 90, but for this it needs to be radians we use. Right, so derivatives. And remember, we're in radians for this. So f of x equals cos 2x, and then we've got our coefficients. So f pi by 2 equals cos 2 pi by 2, which is -1 on your calculator. Or if you just think about it, cos at 180, because that's what that is -1. Right, now, so we're going to differentiate this. So f dashed of x is -2 sine 2x. So f dashed of pi by 2 is -2 sine 2 pi by 2, which is 0. F double dashed x equals, that comes to the front, so -4 cos 2x. So that's -4 cos 2 pi by 2, which is 4. Okay, now I wanted the first 3 terms, but not the first 3 terms. I want the first 3 non-zero terms. So that term there is going to be 0 because it's got a 0 coefficient. So I've got to keep going until I get another coefficient that's not 0. This becomes positive 8 sine 2x. Just a positive there. So f triple dash x is 8 sine 2, which is 0. So the fourth derivative of x would be 16 cos 2x. Which would be -16. So now I've got 3 coefficients that are non-zero. Okay, so let's write down, so the whole point of the derivatives is to get these numbers here. So f of x is going to be, now remember my a is pi by 2. So it's going to be f pi by 2 plus f dashed pi by 2 x take away pi by 2 over 1 factorial plus f double dashed pi by 2 x take away pi by 2 squared over 2 factorial. And remember, we need to go up to the fourth derivative, so I'm just going to keep going with that. Triple dashed pi by 2 x take away pi by 2 cubed over 3 factorial plus the fourth derivative of pi by 2 x take away pi by 2 to the power of 4 over 4 factorial. So there we go. Right, so let's substitute in our coefficient. So f of pi by 2 is -1. So I swap that for -1. So f dash of pi by 2 is 0, so that goes in there. F double dash of pi by 2 is 4, so that goes in there. F triple dashed of 0, sorry, pi by 2 is 0. Right, so let's simplify this. That's going to be negative 1, that's going to be 0, it's 0. Right, so that bit goes away. Right, 2 factorial is 2, so 4 divided by 2 is 2. Right, that's 0, because 0 times anything is 0. Take away 16 over 4 factorial, well 4 factorial is 24, so let's just write that in, simplify that in a minute. Right. F of x is negative 1 plus 2, x take away pi by 2 squared, take away, well they're both in the 8 times table, so 2 and that is my final answer on that one. Okay, so again I've sketched the graphs on this software. So cos 2x is this red line here, as we know. Right, now remember, I'm looking for what happens at pi by 2. So pi by 2 is well, 1.57. So 1.57 is about here. It's about here, right? So let's type in the final bit of this, 3. And can you see that that blue line, which doesn't have a sin or a cos or anything in it, it's just got x's and numbers, perfectly mimics cos 2x. So I know that my Taylor series works